Hi, in this video I would like to explain the working of a Venturi tube, which is used to measure the velocity of a fluid flowing through a pipe. You can see a pipe in the image, and it has got a broad cross section on the left hand side through which the gas is going to come, and it's got a narrow cross section like a neck, and that neck or restriction is called the Venturi in all the engineering applications. There are also two U-tube manometers, one on the left hand side, which is the high pressure side, and one situated at the neck, which is the manometer to measure the low pressure. I'll use a gas, and I assume the gas is not going to react with the mercury, because the gas is going to get into the tube that I have put in there at the high pressure cross section, and even at the low pressure neck you can see that the tube is getting into the main tube, so that it can catch the gas, and the gas is going to travel down that glass tube and press on that mercury. So let's now look at an animation. So as I have put the gas into it, and it's represented by some spherical molecules, the high pressure side depresses and presses on the mercury. Of course, it's high pressure, so the mercury gets pressed down and then rises up the right hand side arm, and the height difference is h1. We can also call it HA to develop the equation later on. On the right side manometer, the velocity increases in the neck region as per Bernoulli's equation. When the velocity increases, the pressure reduces. And because the pressure is very less, it's sucking up the mercury on that left arm of that U-tube manometer, and accordingly the mercury on the right side or right arm of that has come down, because the atmospheric pressure is acting on that open end of the tube. So the height difference H2 or HB describes the pressure of the neck, which is lower than the atmospheric pressure. Now let's look at the equation. So start with the Bernoulli's equation for point A and point B, which is basically an energy conservation equation. The term GH is the potential energy per unit mass. That goes away from the equation because the mean height of point A and point B is the same. So we are left with rho and VA squared. So PA plus half rho VA squared will be PB plus half rho VB squared, as we can see. So get it into the form of PA minus PB. The ultimate job here is to find the velocities of the fluid flow. So we start with the pressure difference between point A and point B. Also use the U-tube equation, where the pressure at point A, the pressure of the gas, is equal to P atmosphere plus rho G into height difference, which is H1 in the image and considered as HB. Once you do that, from the U-tube equation you can find another way of writing PA minus PB, and that's also shown here, and you'll get it in terms of the HA minus of HB. Be careful that the HB was the mercury being sucked up on the left hand side, so it's negative. So in this particular case that I have taken, when it's negative, it will actually land up doing HA minus of minus HB, though it may not always be the case. So once you do that, equate both the previous equations. So you'll get half rho into VA squared minus VB squared is equal to rho G into HA minus HB. Rho